Hello everyone, and welcome to the final session in our course on information theory and complex systems. In this session, I'm just going to provide a short little wrap up to the course. Let's start right back at the start, looking at what our original learning outcomes and reflecting on whether we've achieved these. Our fundamental learning outcome here was to understand the basic measures of information theory, including entropy, mutual information, and their conditional variance, as well as more advanced measures for time series like entropy rate, active information storage, transfer entropy, and so on, and to think about how, and to understand, I should say, how we can use these to analyze and dissect the nature, structure, function, and evolution of complex systems. Going beyond that understanding of the measures themselves, we wanted to actually be able to use or apply these measures. So specifically, our next learning outcome was about developing scientific programming skills that we can use to apply to complex systems analysis and design. Making that more specific, we wanted to be able to understand the design of and to extend the design of a piece of software using the techniques we looked at in our lectures and from our own readings. And in particular here, we're talking about the JIDT toolkit to be able to understand the design of software using those implementations for complex systems analysis and to be able to extend the designs of those templates as well. Furthermore, I want you to be able to apply and make informed decisions in selecting and using the information theoretic measures and software tools to analyze complex systems. So understanding which is the right tool to answer the specific questions that you have, and why is that the right tool, and why should we set the parameters the way that we do, and be able to critique others' work in doing that as well. Moving on to a higher level, I wanted you to be able to create information theoretic analyses of real-world data sets, in particular those in your own domain area of expertise. For example, if you're a biologist, you might now be able to apply these measures to analyze collective behavior in schools of fish, for example, or to look at the interaction between genes in a regulatory network. Whatever your background domain is, I'm sure you've thought long and hard through this course about how you can now take these tools and analyze data in your domain. And finally, I want you to come away with the capacity to critically evaluate investigations of self-organization and relationships in complex systems using information theory, and to be able to critically evaluate the insights provided by these tools. Okay, so not just understand how to do it, but understand what is the right way to do it, how the parameters should be set, how we can interpret the results, and so on. I hope that you have achieved these outcomes. Let's look at how we got there. In our lectures, we started off in a first block, if you will, by covering the fundamentals. We started with an introduction to information theory and entropy, moved on to looking at measuring information via the mutual information, and this gave us the fundamentals to understand what information theory is. We then took that to the next level by looking at how to start applying that more seriously to complex systems. We looked at the JIDT toolkit, we looked at different estimators that we could use for continuous valued data, we looked at more advanced concepts including statistical significance, and we started thinking about how to apply these measures to study self-organization in terms of how information is structured in complex systems. We then took that to another level again, thinking about studying information processing in complex systems as a particular way of modeling and analyzing how information is structured in these ways, including looking at information storage and information transfer. And we finished with a particular deep dive into looking at modeling effective network structure when we only have multivariate time series from a complex system alone. So these three blocks make up the course in its entirety. In each one, we use a number of resources focusing on the core 4 resources being Cover and Thomas, Mackay, the Bossenmeyer and Company Transfer Entropy book, and my paper with the JADT toolkit. And obviously we focused on the toolkit itself as our main way of measuring, of estimating these measures from empirical data. And that's one of the key takeaways from this course in terms of how to actually do that with your own data sets. If you're taking this in one of my formal classes, obviously there are a set of assessments to go with these activities as well to help us achieve these learning outcomes, as well as to test those outcomes as well. There are a number of final messages that I want to leave you with. Firstly, thinking about the context and perspectives that we've taken here. There are many different perspectives that we could take in learning about information theory. So when you need to understand that I've just given you my perspective, I've focused on empirical analysis of complex systems. That's not the same perspective that others will take when they teach you the same concepts. This is my perspective, and that's going to leave a mark, if you will, on how I've delivered that material to you and how I think about that material and how you might think about that material now that you've seen my perspectives on that. Of course, you need to understand that we've necessarily left out a lot that we could have included in a course on information theory, particularly because we've taken this focus on empirical analysis of complex systems. We've left out a ton of the traditional uses of information theory and coding because they're just not in scope for us here. We've left out a lot. We've left out looking at channel capacity at all, including looking at the noisy channel coding theorem. We haven't talked about relating channel capacity to signal to noise ratio. We've barely talked about coding except for the fundamental interpretations of some of our measures and a brief look at Huffman coding. But there's a lot out there for the traditional use of information theory that was just not in scope for us. Furthermore, there are other key uses of information theory in complex systems that I've completely left out here as well, including maximum entropy methods, the information bottleneck approach, looking at sensor actuator loops, and even thinking about phase transitions in complex systems, which is one key application of information theory to complex systems. For that, if you're interested to read about how information theory can be used to analyze phase transitions, you can look at several key examples in the Bossenmeyer and Company book. On the whole, though, I've left these out for the reason that I think you are now equipped to look at these yourself. Okay, I've given you the fundamentals, I've given you some key ways of looking at complex systems using information theory, and I think you can go and do these yourself now. So I actually made a very conscious decision to leave them out of the course for that reason. If you're interested in these, you can go and look at them yourself now. Finally, I left out a couple of key areas of research for information theory and complex systems, including the relationship between information theory and thermodynamics, which is a very hot area at the moment, information thermodynamics. And I also, to a large extent, left out the concept of partial information decomposition, looking at how two sources can hold redundant information about one target, or how they can hold unique information or synergistic information. I hinted about that a lot, and I've said several times now that I think my PhD student Connor Finn has the right approach going forward, and you can look up his work if you're interested. But to a large degree, it was out of scope for us. But I would like to highlight here that there are active areas of research about information theory and complex systems. And for me, that is what continues to be very exciting about this field. Next, I want to emphasize a saying that I've used a number of times in this course already, and you're possibly sick of hearing about it now, but I'll say it one last time. Information theory is all about questions and answers. And that's something that we really need to bear in mind here when we're thinking about using information theory for empirical analysis of complex systems. When you apply one of your estimators to a given data set in complex systems, the estimator will always deliver you an answer. But you need to think, is this answering the same question that I think I'm asking? Okay? That's where this capacity for critical evaluation is really important. Am I asking the question that I want to be asking when I apply this estimator? That's a really important consideration. So I want you to think hard about the question that you want to ask of the data set you've got, and think whether and how information theory can help you get the right answer to that question. Is information theory the right approach to answer that question? Is this particular measure the right one to answer that question? Are my parameters set properly to help me answer that question? And so on. Finally, let me summarize one more time why we're using information theory to analyze complex systems in the first place. The way I would answer that question is to say that information theory is a very, very powerful approach for investigating the dynamics of and relationships within complex systems. There are many pros to using information theory in this way. It's data type agnostic. We can use it to analyze Boolean data from gene regulatory networks, as well as continuous value data from a brain imaging analysis, for example, and have the same meaning for the same measure in both cases. It can find us nonlinear relationships, unlike standard correlations, for example. It's very mathematically rigorous. There's a long history bringing the mathematical rigor to this approach. There are also many features of complex systems that we're interested in, for example, how complex systems process information, that can be measured or modeled or both by information theory. And that's a really important thing for us to understand why we're using information theory here. With all of that said, I do want to raise the fact that Shannon famously argued to restrict the application of information theory just to communications engineering in this 1956 article. As a last activity, I want you to take that article, it's only 1 page long, have a read, and see what you think. Is that what he's really saying? And do you agree with him or not? My opinion on that should be fairly clear by now. Obviously, I wouldn't have run this course at all if I agreed with his perspective. Obviously, I think information theory has a very strong place in being used for empirical analysis of dynamics of and relationships in complex systems. But I think it's very important that you form your own conclusions about that. Okay, that's part of the critical evaluation capacity that I want you to get to. So have a read and have a think about that. What do you think about the opinions that he expressed, and what do you think about the way that I've been teaching you to use information theory for complex systems? Come to your own conclusions about that. So that's it from me. My name is Joseph Lizier from the University of Sydney, and I hope that you've enjoyed taking this course as much as I have enjoyed delivering it. I hope you're excited about taking your new skills and tools and beginning to analyze the dynamics of and relationships within complex systems. I hope that we cross paths in the future. Maybe you'll let me know what you've achieved with these tools. Maybe you'll contribute to the tools yourself. Or maybe I'll end up reading some of the analyses that you've done with these tools. Regardless, whichever way you use this knowledge, I wish you the best of luck in doing so.